Alright, so we've got 3 places to check, but in general, you'll have n products, you'll have n nutrients you care about, and so it becomes an extremely complex problem in terms of the geometry of searching, and it's not clear how quickly you can search the space. So just because we have a procedure, it's not clear how quickly the procedure will work. Now for Calc 3, how do we find maximum and minima on the boundary? What do we do in Calc 3?
Get substitute variable.
I'm sorry?
You get substitute variable.
Sometimes you can try to use things like the implicit function theorem and solve for some variables in terms of the other and work the constraints in. But there is a method in Calc 3 that avoids substitution, which says, I want to optimize, I want to solve something on a boundary. I'm sorry? Lagrange multipliers. So, Lagrange. You've got some surface like this. This is your constraint, g of x equals c. You've got your normal to the surface. And then if this is the gradient of g and this is the gradient of f, this is not a maximum or minimum. The candidates for the maximum and minimum are when the gradient of f aligns with the gradient of g. So you want gradient of f equals lambda gradient of g. And so you'll often look at nice surfaces where the gradient of g is never 0. It turns out Lagrange multipliers, this idea, can help you more than just trying to find the candidates. If you're over here, which way do I want to go if I'm searching for a maximum? Do I want to go this way or this way? Do I want to go down or up if I want to find a maximum? Why up?
I don't know.
So look at maximum is up. So I break my vector for grad f into something in the direction of grad g and something perpendicular to this, tangent to the surface. So this tells me how I'm changing. Now if I force myself to stay on the surface, I can't access this amount of grad f. So the gradient of f is pointing in the direction of maximum change of your function. I want to go straight up, for instance, if the gradient is pointing in the same direction as the gradient of g, but if that's not allowed, I have to stay on the surface. So if I move in this direction, I'm going to be increasing. If I move up, I'm going to be decreasing. So if I want a maximum, I actually want to keep flowing in this direction. So when you do Lagrange multipliers, not only does it tell you a condition for when you have a maxima, but it gives you an idea of how to find it. At each point, if you're not at a maximum or minimum, if you're not at one of these candidates, look and see which direction the gradient of f is pointing. If you want a maximum, go in that direction, tangent to the surface. If you want a minimum, go in the opposite direction. So you can correct this to try to find a way to search the space. We need something like that over here. We need an efficient way to search the space of all points. Okay? And so now this is going to lead into the notion of a feasible solution to a basic feasible solution. So feasible solution is just anything that solves the constraints. A basic feasible will have a few more conditions attached to it. So let's let ax equals b, x greater than or equal to 0, minimize C transpose x. There are a couple of assumptions one typically makes about B. So the first is that, let's say matrix A is m by n. So it has, so it's m rows and n columns. So that means my variable x has n components, and my variable b, my parameter b, will have n components. So b will be in Rn. We typically make the assumption that the system is non-degenerate, that b does not live in a linear combination of fewer than m columns of A. Okay? So assume non-degenerate. B is not a linear combination of, at most, n minus 1 columns. Okay. So now, let's look at the solution. How many components of x do you need to be non-zero? Well, some of this is going to depend on the matrix. We want this matrix to be solvable, so we must be live. So if B is going to be solvable, this goes back to your linear algebra. Sorry. Where does B live?
The row space?
Not the row space. Column space, right? Because B is a linear combination of the columns.
Right, yes.
When you look at AX equals B, this is the same as, let's call it A1 x1 plus AN xn equals B. And I'll draw arrows over these to mean the different columns of A. So this is another good way to view the matrix. Here's A1, here's AN. So B is a linear combination of columns of A. If I tell you it's non-degenerate, if B is not a linear combination of at most m minus 1 columns, then B is a linear combination of either m or m plus 1 or m plus 2 or m plus 3 columns. Do I need m plus 1 columns? No, B has m components. I'm not going to need more than m plus 1. So the dimension of the column space is at most m plus 1. And what I'm basically telling you is I'm giving you, in some sense, a non-degenerate matrix. The matrix has a column space that's full. So I'm going to need at least m columns. In fact, this is going to tell me I need exactly m columns. So, need at least m columns of A. It will always be possible to do this with exactly m columns. Is it possible to do it with more? Sure. I could take two different solutions and multiply the first one by 1/2 and the second one by 1/2. With the first one by 1/3 and the second one by 2/3. Linear combinations of solutions are solutions. But there will always be a solution with exactly m columns. Now we've got to be a little bit careful. Because we're assuming a little bit more. We're assuming that the elements of A are non-negative. That makes things a little bit more interesting. Right? If I want to just solve AX equals B, I can do that, but I might have some negative entries. Negative entries, that doesn't fit the model. We have to have non-negative entries. Okay? So this leads to the notion of what's called a basic feasible solution. AX equals B, and the corresponding columns of A to the non-zero elements of X are linearly independent. Okay? So we will call this a basic feasible solution. If you have a basic feasible solution, do you have a solution? Yes, that direction is not so high. If you have a solution, do you have a basic feasible solution? Can you somehow go from maybe a vector where you have some components that are negative and get rid of the negative? So it's been a while since I've done this stuff. Let me just quickly look and see what's the best way to deal with this. I don't want to, I think what we have to do is we have to go through the standard linear algebra thing where we replace one entry with the other and keep iterating along those lines. Yep, okay. Alright, so unfortunately, just because I have a solution to this doesn't mean I necessarily have a basic feasible. But it turns out, if I have a solution with non-negative entries, I can play a game and get down to just a basic feasible solution. If if a column is a linear combination of the other ones, I can play games.
So you can't have any negative.
I can't have any negatives. It's not going to be considered a basic feasible. So basic feasible are subsets of feasible solutions. How many basic feasible solutions are there? Finitely many or infinitely many? I'm sorry?
Wait, I feel like it's finitely many.
Because the difficulty is the entries are real values. So it's not immediately clear that there's only finitely many basic feasible solutions. Let's first prove that there are only finitely many basic feasible solutions. So again, a basic feasible, non-negative entries, and the corresponding columns are linearly independent. Alright, well,
So the non-negative entries are part of the definition of basic feasible?
part of the definition. It's got to be a subset of feasible solutions. So now, how many ways are there to choose columns? At most, how many choices of columns can I have?
You mean for the solution?
How many choices of non-negative entries of x? Which is equivalent to saying, how many columns of A do I use in my linear combination?
Yeah.
Well,
If you have n columns, bad.
there's n candidates, but if I give you a basic feasible solution, it has some number of columns. It has m columns of A that are being used.
Okay.
So how many ways can I choose m columns from A?
And choosing.
And choose m.
Okay.
Right? Have n choose m possible choices. And that's less than plus infinity. Now, n choose m could be quite large, but it's still a finite number. So all we have to do is show that given a choice of m columns, there's at most a finite number of solutions. If we can do that, since there's only finitely many ways to do this, finite is finite. Alright, so let's think how we would do this. So let's let A prime be the restricted matrix. Sometimes, instead of doing A prime, sometimes they do A sub B to say, we're taking a base from these columns. And now, we have A prime and we have X prime equals B. And we're trying to solve this equation. How many solutions are there to this equation? Infinitely many or finitely many?
We're assuming that A prime is full rank.
A prime is full rank.
We do A prime transpose. Take the inverse.
What if so is A invertible?
No.
What would it mean if A is non-invertible? If A is non-invertible, it would have to have a determinant 0, which means it would have to have an eigenvalue 0, which means there's some vector, such that A prime times that vector is the 0 vector. That means a linear combination, so A prime will be invertible. So there's at most one solution. And then all you have to do is just see, does the solution have non-negative entries? So we're in really good shape. There's at most one solution, and there's at most finitely many possibilities. Great. The problem is, of course, those finitely many possibilities may be too large to look through. And so when linear programming was first being developed, it was thought to be completely impractical, because you'd have to do thousands of calculations an hour. Well, thousands of calculations an hour has been replaced with trillions of calculations a second for a lot of applications. And it's doable. There is an efficient way of searching through the space. And so it turns out that if there is a feasible solution, there's also a basic feasible solution. So I'm not going to go through the proof of that, that's in my notes. But so, lemma 1, there exists feasible solution, then there exists basic feasible. Good. So this tells you that these basic solutions can at least come into play. What do you think lemma 2 is?
We have a basic. Go. If you have a basic feasible solution, you have an optimal solution.
Not quite. Just because you have a basic feasible does not mean you have a basic optimal. What would you love? So what are we doing? We're trying to find an optimal solution. I could search through the space of all feasible solutions to try to find my optimal, or I could search through the subset of basic feasible solutions.
So if there is a optimal solution, it is basic.
Yes. So lemma 2, replace solution, or replace feasible with optimal. Replace feasible with optimal. So think back to the diet problem. If we happen to line up so that our slope was exactly the same as the slope of one of these boundary lines, we have a bunch of points we're indifferent towards. Choose the vertex. What we've just seen in the statements here is that if there is an optimal solution, there's also a basic optimal solution. Do you care? Yes.
Does that mean that any optimal solution is also going to be basic optimal?
No.
Or just that there exists?
That there exists.
And so are you always assuming that the basic optimal is the one that's going to be easier to find?
Yes. Because we can then search through the space of basic feasible solutions. And there's a good way to search through the space of basic feasible. But there could be another solution that is optimal but not basic.
But you just don't care about that.
We just don't care about it because we're indifferent. Okay? Do you care at all if your diet is all hot dog or all hamburger? Do you want to have some variety? Do you have any preferences for taste between the foods? This model completely throws that away. You can try to incorporate secondary constraints like this. Where, as the dictator, not only do you want to keep your people alive as cheaply as possible, you care about their welfare and you want them to enjoy their meals. Okay? Then you want to start putting these things. Well, if you start putting those in, you now have a different objective function. The objective function is no longer just cost. So then the question becomes, how do you handle multiple constraints like this? How do you handle your enjoyment of meal and cost of meal? So that would allow you to distinguish between certain diets. Would you be willing to have a more expensive meal if it tastes a whole lot better? Any Seinfeld fans here? There's an episode where George Costanza hires a secretary, and she explains to him, he's working at Yankee Stadium, that they can switch the type of oil they're using for some of the snacks, and it's only going to cost like ½ cent per thing, so it's definitely feasible. And so yes, it's going to be more expensive, but for the New York Yankees, ½ cent more, for the cost of a unit of popcorn or whatever is insignificant. And so to have something that's healthy or something that tastes better for ½ cent was a worthwhile trade. So the question becomes, in the real world, how do you balance competing issues? So I'll leave that as a homework problem as to how would you try to deal with two different with trying to optimize two things simultaneously. How would you adjust things? So we've got about 10 minutes left. I want to end with the description of the simplex method. And the simplex method is going to tell us how to solve something like this. So I'm not going to go through all the different technical restraints and whatnot. I'm just going to state the simplex method. So phase 1, I think it's given a feasible solution, find a basic feasible solution and prove that none exists. Right. Okay, no, okay, it's find a basic feasible solution or prove none exists. So that's step one of the simplex method. Step two, or phase two, given a basic feasible solution, find a basic optimal or prove none exists. And in fact, the way it proves that none exists is it gives you a sequence of basic feasible solutions where the cost goes to minus infinity. Because if the cost is bounded, then there will be a, I think, basic fees. Well, I'll stop there before I get into trouble. All right, these are the two steps of the simplex method. Find a basic feasible solution or prove none exists. Given a basic feasible solution, find a basic optimal solution or prove none exists. Okay? So here's the proof. Use phase two to prove phase one, then prove phase two. So if you haven't seen this before, something should seem fishy. So yes?
You're kind of backwardly using phase two to prove itself.
Yes. It turns out it's acceptable. Okay, so this is an extremely clever idea. So phase one, find a basic feasible solution and prove none exists. Phase two, given a basic feasible solution, we find a basic optimal. We're going to use that to find a basic feasible solution. If I give you a basic feasible solution, is it hard to find a basic feasible solution? No. So in order for this to have content, I can't be solving the same problem. I'm solving a related problem. So what I do is I take my canonical linear programming problem and I start off with a quest to find a basic feasible solution to it. Instead, I look at a new linear programming problem where I can find a basic feasible solution. Once I have a basic feasible solution, I can then use phase two to find a basic optimal solution or prove that none exists. And that basic optimal solution will turn out to be the feasible solution, the basic feasible solution to the initial problem. So it all comes down to, can you come up with a good related problem where you can just guess a feasible solution? Okay? Let's imagine you are American Airlines. What is your objective? Make money. Alright? There's a bunch of constraints. Some are obvious. You can't have the same flight, the same plane flying two different routes at the same time. Some of them are less obvious. You know, the pilots have to be on the ground for at least so many minutes, you know, after they land before the plane can take off again. So you have a whole slew of constraints. You have different estimated demands of people going from city to city. Can you give me a schedule for American Airlines that satisfies all the constraints?
No.
What?
Sure, why not?
Yeah.
It'll take forever to find.
I want you to give me a solution.
Just fly no planes.
Fly no planes. Fly no planes works. Okay? You're a movie theater.
You're not gonna make money.
Hey,
but like,
hey. Sometimes with the way our government works, you actually make money by not doing things and being paid not to do things. So we will not go there, but one solution for American Airlines is to fly no flights. Let's say you're a movie theater, and you have a bunch of movies to show on screens, and you have different constraints. You can't have the same movie being shown on two screens at the same time. It takes a certain amount of time to clean up different screens. If it's a kid movie, it takes more time because the kids are messy. Can you give me a schedule of movies that works?
Shut down the theater.
Shut down the theater. Right? So there are a lot of problems where you can just see the answer. Okay? So frequently, finding a basic feasible solution is not difficult. One of the famous problems in the subject is the traveling salesman problem. You want to find the minimum distance between the cities. Can you give me a path between the cities? Yeah, go in alphabetical order. Right? Almost surely that's not going to be the optimal solution, but it will be an initial solution. So for many problems, it's actually not hard to find the starting point. And so we will come up with a related problem next time that deals with this and passes it on. Okay. Hopefully the first part of the lecture recorded when the camera shuts down